Navigation is a core skill in search and rescue. While modern tools such as GPS units, smartphones, and mapping apps make navigation easier than ever, they are only tools. Batteries can die, devices can fail, and technology doesn't replace an understanding of where you are and how to get where you need to go. Good navigation skills help us travel safely, locate search assignments, communicate locations accurately, and return home at the end of a mission. By combining maps, compasses, GPS, and terrain awareness, SAR members can navigate confidently in a wide variety of conditions. The goal of this class is not to replace technology, but to help you understand and effectively use the navigation tools available to you. Please remember that this class is only an introduction. The concepts you learn today will give you a solid foundation, but proficiency comes with practice. You are highly encouraged to continue learning and spend time practicing these skills on your own. To begin, we will learn about maps. Not all maps are created for the same purpose. In search and rescue, you may encounter several different types of maps. Some are designed for navigation, some for planning, and some for providing an overview of the search area. A good SAR member should be able to recognize what type of map they are looking at and understand how it can help them accomplish their assignment. Some of the maps typically used in SAR are topographic maps, satellite images, road maps, and search assignment maps. If we could only carry one type of map into the field, it should probably be a topographic map. Topographic maps show terrain, elevation, ridges, valleys, streams, roads, and many other features that help us navigate and understand the landscape around us. Today, we don't just access maps on paper. Through CalTopo and other mapping applications, we can view topographic maps, aerial imagery, satellite imagery, and other map layers directly on our phones and GPS-enabled devices. One of the greatest advantages of CalTopo is the ability to switch between layers or combine them to better understand the terrain and conditions in an area. However, for the purposes of this training, we will focus primarily on paper map navigation. Understanding how to read a paper map and use a compass provides the foundation for all navigation skills and ensures you can continue to navigate even when technology fails. No matter what type of map we're using, there are a few basic elements that help us navigate. At the top of many maps, you'll find information that helps identify exactly what map you're using. Map source tells us who created the map. In this case, it's the U.S. Geological Survey, or USGS. Cooperating agencies identifies other organizations that helped produce or maintain the map data. Map series or product tells us what type of map we're looking at. Here, it's a U.S. topo map. Map name and series identify the specific area covered by the map. In the margins of the map, this may be at the bottom or to one side, we find more information. First is north. Maps are referenced to true north or grid north, while a compass points to magnetic north. The angle between them is called declination. We'll learn how to account for declination later in the class. Next is scale. The scale bar helps us estimate real-world distances. It allows us to answer the question, how far is it from here to there? You'll also see a map scale ratio, such as 1 to 24,000. This means one unit on the map equals 24,000 of the same units on the ground. Contour lines are an important map feature. They are lines on the map that connect points of equal elevation. They help us see the shape of the land in 2D. The contour interval is the vertical distance between the contour lines. Always check the map margin to find the contour interval. When contour lines are far apart, the land is flatter and travel is easier. Contour lines that are close together reflect land that is steeper, making travel harder and slower. How would you determine the elevation of this quarry? This map has contour lines that are 40 feet apart. There are 200 feet between each of the darker lines. The quarry sits on a dark line, so we can see its 200 feet up to the next dark line. There are 200 feet between each of the darker lines. The quarry sits on a dark line, so we can see its 200 feet up to the next dark line. Then there are 4 more lines before we reach the peak. 4 lines at 40 feet is 160 feet. Add the first 200 feet and we have 360 feet. We can then subtract 360 from the elevation of the peak, 3,380 feet, and we know the quarry is at about 3,020 feet. Topographic maps often label the elevations of important features, such as mountain peaks, hilltops, passes, saddles, and low points. These labeled elevations serve as reference points across the map. However, most locations won't have an elevation printed next to them. That's where contour lines become useful. Once you know the map's contour interval, you can determine the elevation of nearly any point on the map. Simply start from a labeled elevation and count the contour lines up or down until you reach your location. Now let's look at the margin of a map printed from CalTopo. Here we can see many of the same map elements we've already discussed. A CalTopo map will include important information such as the datum, UTM grid, map scale, and the difference between true north and magnetic north. The QR code on a CalTopo map can be scanned to open a digital copy of the printed map on your phone. Other map features, such as UTM grid lines, contour lines, roads, trails, and imagery, come from the map layers selected by the person creating the map. Those layers can be adjusted depending on what information is most useful for the mission or training. Now that we've introduced some map basics, it's time to talk about coordinates. There are several coordinate systems used for navigation today. Each coordinate system has strengths and weaknesses. Latitude and longitude is the most widely recognized coordinate system. It is especially suited for aviation and maritime navigation, where global coverage is crucial. However, the coordinates can be lengthy and are not always easy to plot on a paper map. UTM uses a grid measured in meters, making it easy to estimate distance, plot locations, and communicate coordinates over the radio. USNG and MGRS uses the same underlying grid as UTM. No matter which system is used, the most important thing is that everyone involved knows which coordinate system is being used and communicates it clearly. In Pend Oreille County Search and Rescue, we will primarily be using UTM coordinates. They are easy to read, easy to communicate over the radio, and work well with both maps and GPS units. Before we move on and focus on UTM coordinates, there are a couple of things worth mentioning about latitude and longitude. Lat-long is the coordinate system most commonly used by aircraft. If we request air support, it is helpful for coordinates to be provided in a latitude/longitude format. Also, Google Maps can be quite helpful when driving to a location where a search may begin. Decimal degree coordinates can be entered directly into Google Maps to navigate to a location using public roads. Now, let's get back to UTM. UTM divides the Earth into 60 longitudinal zones, each spanning 6 degrees. UTM zones are numbered consecutively. In the U.S., Zone 1 includes the westernmost point of Alaska, and the state of Maine lands in Zone 19. Within each zone, locations are identified using a grid, with distances measured in meters. Each grid is 1 square kilometer and can be further divided into 100-meter squares. UTM grids are included on all U.S. topo maps published by the USGS after 2010. Let's have a quick lesson in plotting coordinates in UTM. A complete UTM coordinate includes a grid zone designator, an easting, and a northing. The easting measures how far east you are within the zone. Note that the central meridian of each zone is given a value of 500,000. while the northing measures how far north you are from the equator. UTM coordinates are always written with the easting first and the northing second. The easting is 6 digits, while the northing is 7 digits. A leading 0 is added to the easting to keep formatting consistent.
Let's plot the coordinates for this peak.
The first step is to identify the grid square that contains the landmark. The first 4 digits of both the easting and northing come directly from the map margins. Our job is simply to determine the last 3 digits. We'll start with the easting. Remember, we always read right, then up. Find the first easting grid line that touches the left side of the grid square containing the peak. In this case, that grid line is labeled 0487000. The first 4 digits, 0487, become the beginning of our easting coordinate.
This is called a coordinate template, or a grid tool. The grid tool helps us determine the final 3 digits of the coordinate. To be accurate, it must match the scale of your map. The grid tool helps us determine the location we are plotting by dividing our 1 kilometer square into smaller 100 meter square sections. To find the 4th digit of our easting, we will count the boxes of the grid from left to right, starting with 0. We can see that our peak lies in the 3rd box.
The last 2 digits are an estimate of the point's position within that 100-meter section. They represent the remaining distance in 10-meter increments. Because we're estimating by eye, these final 2 digits are an approximation rather than an exact measurement. The middle of the square would be 50%, so use your best judgment. It can be a bit of a guess. For this one, we will estimate that our peak is 75% of the way across the 100-meter square. 75 becomes the last 2 digits of our easting. Now we repeat the process for our northing. Remember, the first 4 digits come directly from the map margins. Moving up the map, we stop at the first northing line that touches our grid. This tells us our first 4 digits. This time, to find the 5th digit of our northing, we will count the boxes of the grid from bottom to top, starting with 0. We can see that our peak lies in the 7th box. 7 becomes our 5th digit. Now, we estimate our 10-meter increments. It looks like our peak is about 40% of the way up our square. So 40 becomes the last 2 digits of our coordinates. Here are the final coordinates for our peak. Remember, our entire county lies in Zone 11U. Let's check CalTopo and see how we did. Not bad at all. When using a UTM coordinate template, a carefully plotted point is typically accurate to within 25 to 50 meters, which is more than adequate for most search and rescue navigation tasks. So far, we've learned how to identify a UTM location on a map and how to plot coordinates. But knowing where a point is only solves half the problem. The next question is, how do we get there? That's where the compass comes in. In the next section, we'll learn how to use a compass to determine a bearing and confidently navigate from one point to another. Before we start using a compass, let's become familiar with its basic parts and what they do. There are many different styles of compass. We'll focus on a mirror-sighting baseplate compass with a declination adjustment screw, allowing the compass to be set for our local magnetic declination. The rotating azimuth ring is used to set and read bearings. Inside the housing, the orienting arrow and orienting lines help align the compass correctly. Luminous lines are located at the 12 o'clock and 6 o'clock positions of the ring, with 12 o'clock position being the heading to follow once a bearing has been set. The sighting mirror allows you to accurately aim at distant landmarks while simultaneously reading the compass, greatly improving accuracy. It can also be used as an emergency signaling mirror. The clear base and map scales make it easy to measure distances and plot bearings on a map, and the magnifying lens helps read small map details and coordinate markings. All of the instructions we are about to give assume you are using a compass that has already been adjusted for local declination. Once the declination adjustment screw is set for your area, the compass automatically accounts for the difference between magnetic north and true north. That means you do not need to do extra calculations each time you take a bearing. You can use the compass on the map, use it in the field, and move back and forth between the two without having to rethink declination each time. This keeps the process simpler and helps prevent frustration and navigation errors. Now, let's orient a map in the field so that north on the map is actually pointing north. First, set your compass to 0 degrees. Then, take your compass and line up the edges or base plate lines with the north-south grid lines on your map. To orientate the map, rotate both the map and compass together until the red compass needle and the red orientating arrow match up. This is sometimes referred to as putting red Fred in the shed. And that's it. You've orientated the map. Now we'll learn how to plot a bearing on a map using your compass. Let's say we are at Conklin Lake and want to hike in a direct route to No Name Lake Campground. Use a straight edge to draw the line of travel on your map. Be aware that when plotting a bearing on a map with your compass, you will always ignore the compass needle. Now, line up the edge of your compass baseplate to the line you've drawn. Turn the azimuth ring so that the orienting lines are parallel with true north. The bearing is read at the luminous line near the hinge of your compass. Following this bearing will lead you to No Name Campground. We will get into some specific techniques for following a bearing in a moment. What if we need to retrace our steps? Or what if we were standing at No Name Lake and wanted to travel back to Conklin Lake? One option would be to rotate the compass and repeat the entire process to determine a new bearing. However, it's much faster to use a reverse azimuth, which points you in the exact opposite direction. There are several ways to determine a reverse azimuth. Option 1. Read the bearing directly across from your original bearing on the azimuth ring. This is the mark at the opposite side of the compass, what we've been referring to as the 6 o'clock position. Option 2. Instead of putting red Fred in the shed, place the white end of the magnetic needle inside the orienting arrow, or shed. The direction of travel arrow will now point along the reverse bearing. Option 3. Use a little math. Add 180 degrees to the original bearing. For example, a bearing of 56 degrees becomes 236 degrees. If the original bearing is greater than 180 degrees, simply subtract 180 degrees instead. This method always gives you the reverse azimuth. Now let's get back to our journey. We know the bearing we need to follow to reach the No Name Lake Campground, but there's one more important piece of information we need. How far away is it? Knowing the distance helps us estimate travel time, manage our pace, and ensure we have enough daylight, water, and energy to complete the trip safely. Fortunately, every topographic map includes a scale that lets us convert map measurements into real-world distances. There are several ways to use the map scale. While a ruler works well, you don't have to carry one in the field. A compass baseplate, a piece of string, your compass lanyard, or even the edge of a piece of paper can all be used to measure distance accurately. In this example, we've marked the length of our route on a scrap of paper. Next, place the paper along the map's scale. Since we're measuring in miles, align the starting corner of the paper with 0 on the scale. Make a second mark on the paper at the 1.5-mile mark. Now slide the paper so the new mark lines up with 0 on the scale. Our original end mark now falls very close to the 1.5-mile mark again. That tells us our route is approximately 3 miles long. Now we have everything we need. We know the bearing to our destination, and we know how far we need to travel. The next step is following that bearing accurately. First, confirm that the correct bearing is set on your compass. Hold the compass level in front of you and open the mirror so you can see both the compass housing and the area ahead. Slowly turn your body until the red end of the magnetic needle is aligned with the orienting arrow, or, as you'll often hear, put red Fred in the shed. Once the needle is properly aligned, look through the sighting notch and choose a distinct landmark, such as a tree, large rock, or stump that lies directly on your bearing. Walk to that landmark, then stop and repeat the process by selecting another landmark farther ahead. This technique is much more accurate than trying to walk while constantly looking down at your compass. By moving from one landmark to the next, you'll stay on your bearing while keeping your attention on the terrain around you.
What if you're asked to take a bearing on an object or landmark? First, hold the compass level at eye height. Look through the sighting notch and aim at the landmark. Rotate the azimuth ring until the red end of the magnetic needle is inside the orienting arrow, red Fred in the shed. Read the bearing at the index line. There may come a time when you know where you want to go, but you're not exactly sure where you are. Perhaps you've left a trail while searching for a subject, GPS reception has failed, or you've become disoriented in unfamiliar terrain. Before you can navigate to your destination, you first need to determine your current location. Fortunately, if you can identify a few prominent landmarks around you, a map and compass can help you pinpoint your location with surprising accuracy. This process is called resectioning, and it's an important skill for every SAR member to understand.
Start by looking around you. Find 2 or 3 landmarks you can also identify on the map, such as peaks, lakes, road bends, towers, or trail intersections. Take a bearing to the first landmark. Point your compass at the landmark and turn the azimuth dial until red Fred is in the shed. Find that landmark on the map. Place the edge of your compass base at the landmark and rotate the entire compass, not the bezel, until the orienting lines on the base plate are parallel with true north on the map. Draw a line along the edge of the compass from the landmark in the direction of your position. Better to make the line too long rather than too short. Repeat this process with another landmark. Take a bearing on a landmark, find it on the map, and draw another back bearing line. Find where the lines cross. Your location is near the point where the lines intersect. If 3 landmarks are available, the result will be even more accurate. Congratulations! You've completed this introduction to land navigation. Over the course of this class, we've introduced concepts like how read a topographic map, understanding contour lines and terrain features, measuring distances, working with UTM coordinates, plotting locations on a map, taking and following compass bearings, determining your own location, and navigating from one point to another. We've covered a lot today, but these skills all work together. Maps, coordinates, and a compass each play a role in helping you navigate safely and accurately. The key to becoming proficient is practice. Take these skills into the field, use them often, and build your confidence before you're called upon to use them on a real search mission.